So it's my great pleasure to introduce the second tutorial speaker, Ciaran McCreesh, who will tell us about no less than subgraph finding algorithms and presumably proof logging for such algorithms.
Yep.
Please, take it away.
So there is a fair amount of duplication in this with the previous talk, so we hope that by the time you hear things twice, you will half understand it. And when Matthew repeats everything again, that's the third time when you'll be out. Okay, maximum clique problem. So I'm going to give you a graph, and we're looking for a clique. So a clique is a set of vertices where everything in the set is adjacent to everything else in the set, and we want this to be as big as possible. So in this graph, I can show you a 4-vertex clique, and the interesting question is whether it's anything bigger. Okay. It turns out people want to solve the maximum clique problem in practice for a whole bunch of applications. So there has been quite a lot of effort put into developing algorithms for this. Not quite as much as SAT solving, but you know, there's maybe 1 or 2 papers a year on cliques at this point. So here is a rough idea of how a lot of maximum clique algorithms work. We're going to pick some vertex v, and we're going to decide either v is in a maximum clique or v is not in a maximum clique. And we're going to branch. Suppose v is in the clique, we just throw away every vertex not adjacent to v. And then if we have some vertices left over, we're going to recurse and try again. Alternatively, v is not in the clique, so we're going to throw v away and pick another vertex and branch on that. So this is a basic idea behind the algorithm. So we have 2 data structures. In the literature, these tend to be called C and P. C is the set of vertices that we have accepted so far. And these vertices always form a clique, not necessarily a maximal or maximum clique, but everything in C is adjacent to everything else in C. And then we have a set of potential vertices, this is P. The P set is everything that we haven't thrown away yet. And the invariant we maintain is that every vertex in P individually is adjacent to every vertex in C. So for any vertex in P, we are always allowed to pick it and add it to the clique. And we always maintain these 2 data structures and properties during the execution. One more thing, we're solving an optimization problem. So we're going to do branch and bound. About to kick me off. Good. So I'm going to remember the biggest clique that we've found so far. Now, if at any given point, the number of vertices in C plus the number of vertices in P is less than or equal to the number of vertices in the biggest clique that we found so far, we definitely know we're not going to be able to find something bigger, so we just backtrack immediately, we don't keep going. It turns out that the number of vertices in P is not a very good bound. So here is an interesting property. Given any subgraph, we can color that subgraph. Suppose we can color that subgraph using K colors such that adjacent vertices must be given different colors. Then the number of colors we use is also a bound on how much further we can grow the clique, because every vertex in a clique must be given a different color. Now, producing an optimal coloring is even harder than solving the clique problem in practice. But we can produce, for example, a greedy coloring very, very efficiently. Slightly more expensive than just counting the number of vertices in P, but not very much more expensive. So at any given point, rather than size of C plus size of P as a bound, we can produce a greedy coloring of just the vertices remaining in P, and we can use the number of colors that we use plus the number of vertices in C as a bound. Does that make sense? So this takes us up to about 1997 for clique solving. So since then, people have come up with better bound functions. You can produce colorings in different ways. You can do things that are better than a coloring. Coloring is not the strongest possible bound. We have very good vertex selection heuristics. So when I tell you to branch on a particular vertex, we have very clever ways of doing this that seem to work very well in practice. We have very efficient data structures, so a lot of these algorithms are bit parallel. So throwing away all the non-adjacent vertices can be as fast as a single clock cycle on modern hardware. Producing a coloring, we can produce colorings of fairly large graphs in under a microsecond. There's a lot in how you get these solvers to run efficiently. Another thing is solvers will often start by running local search for a brief amount of time to try to find a really strong candidate quickly. Turns out I don't really need to explain any of these things to you if all I'm trying to do is teach you about proof logging for clique solving. So we can stick with a simplified algorithm and we're still giving you a fairly realistic idea of what's going on. So here's some demotivation. My first experience of doing research was a summer internship with Packet Processor. I was re-implementing a clique enumeration algorithm from the literature, so rather than finding the biggest clique, find me all maximal cliques. There are papers that have tabulated results for benchmark instances, saying for each of these standard benchmark instances, we found the following number of cliques, or we couldn't solve it in time. My code was producing the wrong answer on a few of these instances. I spent a month working on this. Published answers were wrong. I sent an email to the authors of the paper, and they said, I reproduced the bug, so I was confident. They didn't publish their source code, but I managed to reproduce the bug in their code so that I could say, this is, if I do this, I get the wrong answers. And they said, oh, it's only a conference paper, it doesn't really matter. They then went and published the journal paper that had the same mistake in it. And by the way, their runtimes on those problem instances were quite a lot off if you fixed a bug. Their solver was actually throwing away a huge number of solutions. Anyway, I moved on. 5 years later, I had a grant for supercomputer time. I was trying to use computational experiments to understand the empirical hardness of maximum clique. So for those of you who know about phase transitions, I was trying to do phase transitions for optimization. I solved 1 billion clique problem instances using a state-of-the-art clique solver. For about 1,000 of these instances, the state-of-the-art clique solver was producing the wrong answer here. And it turns out if you're trying to understand which instances are easy and hard, and if the solver is cheating to solve some of these instances, it's really hard to get meaningful scientific results. So, I want to carry on this empirical understanding of solver performance experiments, but I don't think I can do this until solvers stop having bugs in them. So I'm taking a 10-year detour to completely eliminate all bugs in all combinatorial solving, so I can go back to doing what I want to do. A few years ago, this would have sounded like a crazy idea. So, as we heard earlier, proof logging. We have input, we feed it into the solver, and the solver spits out an answer. And we take the existing solver, we add a few print statements to it, and the solver prints out a proof. We take this input and we feed it into the proof checker, and the proof checker either says, yes, you have given me a valid proof, you can trust this answer, or it says, no, potentially there's something wrong. If it says no, it might mean the proof checker ran out of memory. It might mean that the answer is correct, but there's a bug in the proof writing code. It might mean that the answer is correct, but you cheated to reach it. It might mean that the answer is wrong. So a no answer from the checker doesn't really give you any information. But if the checker says yes, you are very, very sure that you've got an answer that you can trust. Just a brief detour on what is a proof. This is possibly the shortest published maths paper. So a search on an old computer yielded this equation as the smallest instance in which 4/5 powers sum to a 5th power. This is a counterexample by Euler. So how confident are we that this paper is correct? Well, we could get a calculator, we could check this sum. This is relatively easy to verify, so we're happy. So let's say that this is the smallest instance. So how do we know that we didn't actually skip over some instances? So we can ask ChatGPT. ChatGPT knows about this paper. It can actually go and find a solution and it tells us that yes, it's okay, it checks out, so we can trust this, right? Except that that number is smaller than that number. There is no way this is right. In fact, if you add those things up, that doesn't work. So it very confidently tells you, yes, I checked the solution, it did not check the solution. In this case, it's an integer precision error. It's not a huge big deal, but still, ChatGPT did not check the solution that it said it checked. You can also ask it, how do we know there aren't any smaller solutions? This is some premium quality bullshit here. This is, you know, we've tested lots and lots of bigger things, but we haven't found any smaller solutions. But all of this looks plausible until you think about it slightly. I did ask ChatGPT to generate me this drawing here. It says unbelievable there. So I'm quite happy with that. Okay, let's do this properly. What is a proof? We're going to start with some facts about the problem, which we assume are true. At each step, we're going to derive a new fact from the existing facts in a way that is easily checkable if we agree with each previous fact. And we're going to finish by deriving what we want to show. So for maximum clique, we're going to start with the definition of a maximum clique and with the properties of our graph. And I need to show you two things. There is a solution with omega vertices, where omega is the maximum clique size. And there is no solution with more than omega vertices. Okay. And if I can do this, I've convinced you that I've given you the size of the maximum clique in the graph. So let's think about a very simple clique solving algorithm and just what an ad hoc proof might look like. So if we pretended we didn't know about VeriPB, what might we want to do? We could start with a header in the proof file. We'll just write this out. We're just adding print statements to our solver. Now let's think about what the solver might do. The solver might decide to branch accepting vertex 12. And as soon as it's decided it's accepting vertex 12, so our C set contains a vertex 12, we're going to reject from the P set everything that is not adjacent to vertex 12. Okay. So any of these vertices that I've grayed out, we're going to reject. Okay. Our C set is now 12, and our P set is 1, 6, 7, and 9. Suppose now we branch again, and we also accept vertex 7. We're going to filter out from the P set, and we're going to throw away some more things. We're not writing anything in the proof log yet, we're just doing some branching. We are left with 6 and 9 that we can pick to potentially extend our clique. Suppose we accept 9. Well, at this point, our P set is empty. We can't grow the clique any further. So in fact, we have found a solution. We don't know that it's optimal, but we know we have found a valid solution. So we're going to write this into the proof log file. We're going to say, okay, here is a solution. The proof checker could easily go away and check that, yes, this is in fact a valid clique and it has 3 vertices. From now on, we are only looking for a clique that has 4 or more vertices in it. So what will happen? We've branched on 12, 7, and 9. So we're going to backtrack slightly. We're now at this point, we've accepted 12 and 7. We've already explored vertex 9, only vertex 6 is left as feasible. But if you think about this, okay, having accepted 12 and 7, and we've already backtracked from vertex 9, now, there's no way this has a greater than or equal to 4 vertex in here. So we're going to backtrack from having accepted 7 and 12. I'm not going to write this in the proof, I'm just going to say, okay, backtrack from having accepted 12 and 7. We end up in this state here, and in fact, I've illustrated this by deleting the 12, 7 edge. If you think about it, saying we can't accept 12 and 7 at the same time is the same thing as saying, really, you're allowed to assume that these 2 vertices are non-adjacent. So I'm just illustrating this by deleting the edge. So we're now in this state. We've still accepted 12. We've done one backtrack step, accepted 12. Individually, we could now accept 1, 6, or 9. But if you look at this, this isn't going to work. None of these vertices are adjacent. So our solver isn't even going to try branching. It's going to say, obviously, we can't do the 4 vertex clique. And we're going to backtrack from having accepted vertex 12, and we write this in the proof log. At this point, we've decided vertex 12 is not present in any clique that has 4 or more vertices. So I'm deleting the vertex entirely from the graph, which is how I'm showing this. Okay. Now we're going to do some more branching. Let's say I branch from vertex 11 and vertex 10. I end up in this state. I only have 1, 3, and 9 feasible. You see this? These 3 vertices can all be given the same color. So I've accepted 10 and 11. And then 1, 3, and 9 can all be given the same color. So I'm definitely not going to find a 4 clique here. The best I can get is 3. So I'm going to backtrack from accepting 10 and 11. Again, this is sort of saying I can delete this edge entirely from the graph. This point here, I've accepted 11. I have 1, 3, 7, and 9 left. You can see this is too colorable. Let's see. Those 2 vertices have to be given different colors, but then these vertices are free. So again, I'm not going to get a 4 clique. I can backtrack and I can delete vertex 11. Now maybe we branch accepting 8, accepting 5, accepting 1, and accepting 2. We've found a 4 clique. I'm going to log it as a solution. From now on, we are looking for a clique with 5 or more vertices. I backtrack from the solution. We're in the state we've accepted 8 and 5. We only have 1 and 2 left as potentially feasible. When we only have 4 vertices, we can't get a 5 vertex clique. We backtrack. We're now in this state. We only have 4 vertices. We can't get a 5 vertex clique. We backtrack. And then at this point, the solver will sort of stare at this graph briefly, and it will say, this graph is 3 colorable. It's 3 colorable. We can't get a 5 vertex clique. So we're going to backtrack, having made no guesses at all. And we're going to conclude the proof by saying, okay, the maximum clique size is somewhere between 4 and 4. I'm specifying both upper and lower bounds just in case we ever want to do partial proofs. And I'm going to say this is the end of the proof. So have I convinced everybody that the maximum clique in the graph has 4 vertices? Is this a reasonable proof? Okay. I don't really want to have to write yet another proof checker. Writing a good proof checker is hard work, as people on that side of the room will tell you. So let's reuse VeriPB. Problem here is VeriPB works with pseudo-Boolean problems, graphs. So what we need to do is produce, yes?
Excuse me, but can you please go back to the previous slide?
Yeah.
What you have here looks like a derivation rather than a proof. It is just a series of steps, but
Yes.
you don't know whether, or maybe you do, but my question is, there can be other derivations that produce the same result.
Yes.
Maybe the permutation of steps.
Yes.
With some different choices. So,
Yes.
and there can also be some steps in here that are not necessary. I don't know, I'm just asking. Are there any steps in there that are not necessary to get the result?
Yes, I could delete about, well, for starters, if we'd found this solution faster, then we would have a shorter proof. In fact, for this particular problem instance, a modern clique solver will solve this without guessing. It will 4-color the initial graph. So yeah, there are definitely shorter proofs that a better solver could come up with. What I'm claiming is that for our definition of a proof being a sequence of steps where you can verify each individual step, this is a proof. It's not the best proof, it's not the shortest proof.
Okay, but then I'm sorry, I need to formulate better my point. For me, the difference between the derivation and the proof is that even if the proof does not have to be the shortest,
Right.
but in the proof, all the steps are needed to get the result.
Right.
So if I take one out, it doesn't work. Instead, in the derivation, I can have many steps that eventually do not contribute to the result.
Yep.
So that the proof in general will be something smaller extracted from the derivation, even if the proof is not the shortest one, is not the optimal one. So I guess the question here is, this is a proof or a derivation, that is, all those steps are needed to get the result or not, or maybe for this kind of problem and language, we cannot tell, and this distinction I'm making from theory proving perhaps doesn't make sense.
So we would use the phrase untrimmed proof, where you're saying derivation.
Okay.
And we would use the phrase trimmed proof, where I guess technically a trimmed proof does not entirely guarantee that you really need each step, but a trimmed proof is, after we've produced the proof, we can run it through another piece of software that sort of runs the proof backwards and throws out anything that you didn't actually need to get there. So we would view this as a separate step.
Thank you.
Okay, so we want to use VeriPB, but we have to work with pseudo-Boolean problems, not cliques. So what I need to do is come up with a pseudo-Boolean representation that is so obvious that we all agree that it absolutely, definitely means the same thing as solving the maximum clique problem. So I'm not trying to come up with a good pseudo-Boolean encoding here. I'm trying to come up with obvious pseudo-Boolean encoding that can't possibly be wrong. I will go over this very quickly given the lack of time and that Jakob already told us. Pseudo-Boolean problems, we have 0, 1 variables. We have variables can be negated, which is in syntax. Constraints are integer linear inequalities. Okay, so a pseudo-Boolean encoding for clique. We have 12 vertices here. I'm going to give you variables x1 through x12. x1 means that x1 being true means that vertex 1 is present in the clique, and so on. We want to maximize the number of vertices that are present in the clique. VeriPB works with minimization, so we're going to minimize the number of vertices not in the clique. Okay. For every edge that is not, so for every non-edge in the graph, so every pair of vertices that are not adjacent, we say that we cannot take both of these vertices at the same time. So, for example, vertex 1 and vertex 3 are not adjacent. So I want to say that x3 plus x1 is less than or equal to 1. We have to write this as a greater than or equal to. If you stare at it for a second, minus 1 x3 plus minus 1 times x1 is greater than or equal to minus 1 means the same thing here. So for every non-edge, I'm going to have one of these lines in the file. Now, Jakob told you earlier that every constraint gets a number. The way that VeriPB works, this will be constraint number 1, constraint number 2, constraint number 3, constraint number 4, etc. This is a bit hard to read. So we can also give a constraint a text label. So I'm going to call this constraint no edge 1, 3. If you don't like these text labels, you can pretend that they correspond to numbers. This is what's happening. But for convenience, I'm putting these labels on. And yes, we're going with a slightly different workflow. So we are trusting the solver to produce the pseudo-Boolean encoding B input, at least for now. Okay. So let's try using what was in the previous slide to translate this just as a syntactic translation from our ad hoc proof format to a VeriPB proof. We start with a header. Whenever we find a solution, we use this sol I command. So this means I have a solution, check it, give me a solution, proving constraint. And I just need to list the vertices that are actually present in the clique. VeriPB is smart enough to know, okay, if I set 7, 9, and 12, all the other vertices are obviously false by unit propagation. So I don't have to list out everything. And I'm going to tag this line, I'm going to say, so whenever we have a line in a proof, it also gets a constraint ID. I'm going to give this line a name because I'm going to use this later. This is all the at means. Whenever we backtrack, so I'm saying I have accepted 12 and 7, it didn't work in backtracking. So I want to say that at least one of 12 or 7 is false. So either not 12 or not 7 is greater than or equal to 1. So again, this is just syntax. A backtrack constraint is just saying at least one of these vertices has to be false. So I turn all my backtrack lines into these rep constraints. backtracking from a root node is saying that the sum of 0 variables is at least 1. So this is our notion of contradiction. And again, we have a conclusion at the end of the proof. Remember, we're doing a minimization problem, so I'm saying that there are 8 vertices not present in the clique. So I can take my proof, I can feed it into VeriPB, and VeriPB says, nope, verification error. Line 6, the constraint is not implied by reverse unit propagation. VeriPB is very nice. It has a trace mode. This is where we are. VeriPB has a trace mode, so you can see it will read it. It will say, oh, here's my constraint ID 1, constraint ID 2, etc. When we get to a solution, it creates this, okay, we're looking for at least a 4-vertex clique constraint. We get to line 6, which says, okay, reverse unit propagation, backtracking from x10 and x11. This didn't work. Thinking about what our solver did, we said, okay, we've accepted these 2 vertices. This leaves us these 3 vertices. And we can see that this graph is 1 colorable, so we can backtrack. VeriPB is not smart enough to work this out on its own. This fact does not follow by reverse unit propagation. In fact, we can even say trace failed to VeriPB, and it will tell you here, okay, you asked me to backtrack from setting vertices 10 and 11. If I set both 10 and 11 to true, then, well, vertex 12 we rejected earlier in the proof. 6 isn't adjacent, 7 isn't adjacent, 8, 4, 5, 2, these are not adjacent. And these are all of the facts that VeriPB was able to figure out. And it's looking at this and saying, this isn't enough to let me derive a contradiction. Okay. So, what do? We have to help VeriPB somehow. What specifically we're saying is, vertices 1, 3, and 9 can be colored using at most 1 color. And each color class contributes a score of at most 1 to the objective variable. So, we are saying that the solution improving constraint cannot be satisfied if we have accepted both vertices 10 and 11. So let's think about this. If we take this solution improving constraint, so we're saying we have to get at least 4 vertices out of here. And suppose we could magic in an at most 1 color constraint over this color class. So I want to say you can take at most 1 of 1, 3, and 9. So I'm saying at least 2 of the 3 have to be false. And suppose we could add these together. What would we get? Well, we'd get x1 plus not x1 plus x2 plus x3 plus not x3 and so on. It's greater than or equal to 6, so 4 plus 2 is 6. x1 plus not x1 equals 1. x3 plus not x3 equals 1. x9 plus not x9 equals 1. So this simplifies to get us 2, 4, 6, 7, 8, 9, 10, 11, 12. And from this point, if you set 10 and 11 to be true, then, well, 12 we'd already said we've rejected vertex 12, and all of these will unit propagate to false. So really we're saying that 2 is greater than or equal to 3. So if somehow we could get this constraint into the proof, then VeriPB would be happy. First thing we can do, there is a rule that says A stands for either assert or assume. I think we're still arguing about this. It should definitely be assert. What it says is, trust me that this constraint is true. So I'm just going to add in a line here that says, trust me that most we can get 3. And it turns out we'll have to do the same thing a bit later on in the proof where we do some color class reasoning as well. At this point, I'm going to have to say, trust me, you can get at most 2 at this point. We can take these, we can put them into the proof, and VeriPB is now happy. It says verified bounds. Warning, the proof used unchecked assumptions. And this is fair. In particular, coloring in general is NP hard, so we shouldn't expect VeriPB to do it. We might have put a lot of effort into getting a really, really good coloring, so we should not expect the proof checker to understand how we got this coloring. Let's try something a bit better. Rather than doing this magic derivation using the objective constraint, what if we could take the at most 1 constraint, the color class, and say add the objective variable to this at most one constraint. So constraint ID -1 always means the previous constraint in the proof. So now I'm saying, okay, this is a color class, so I can pick at most one, add it to the objective. And the same thing later on in the proof, I'm going to tell you that 1, 3, and 7 can all be given the same color, 2, 4, and 9 can all be given the same color, 5, 6, and 10 can all be given the same color. And I'm saying take the objective and add these 3 color classes on. So I'm doing a 3 colorability proof later on. So at this point, this is a slightly simpler proof. But we can check and it still works with VeriPB. But at this point, now that I'm telling you what the color classes are, now that I'm saying these 3 vertices form a color class, this is efficiently checkable. So maybe we could add a VeriPB rule that lets us recover an at most one constraint. The good news is we don't have to. VeriPB already has such a rule. It's the cutting planes part of the system. Let's say we take the not x1 and not x6 constraint, the not both x1 and x6. So the non-edge constraint for vertices 1 and 6, the non-edge constraint for 1 and 9, and the non-edge constraint for 6 and 9. Add them together. We get 2 not x1 plus 2 not x6 plus 2 not x9 is greater than or equal to 3. I'm going to divide this by 2. So I get not x1 plus not x6 plus not x9 is greater than or equal to 3 over 2. Now these are integer variables. So if we think back to the division rule, I can round this up. I'm telling you that at least 2 of these have to be false, which is what we were looking for. We're saying an at most one is true. And it turns out that this technique generalizes to any color class. So for any color class that you want to introduce, we can do this. Using a sequence of additions, divisions, and multiplications. We use every non-edge constraint exactly once in this derivation, and we use slightly fewer than the number of vertices divisions and slightly fewer than the number of vertices multiplications. I claim that this is as efficient as we could possibly get, because if we didn't use any of the non-edge constraints, we wouldn't actually have an at most one. So somehow this is a very efficient as possible derivation of an at most one constraint from what we have. The other nice thing is that solvers don't need to understand why this works. You can write a simple for loop that spits out text, literally print statements in a for loop that outputs this poll line. You do not need to do any pseudo-Boolean reasoning inside your clique solver. It is purely print statements in a for loop. So we can put this in, and we end up with something like this. It turns out we were doing color class reasoning in a couple of places earlier, and it just so happens unit propagation works here. But I can put these in now just using these poll statements. So take the non-edge constraints, add them together, divide the whole thing by 2, add it to the objective. And then down here, we're dealing with 3 color classes. Add these things together, divide by 2. They're still on the stack. Add these things together, divide by 2. Add these things together, divide by 2, and add them all up with the objective. We can run this through VeriPB. No more untrusted assertions, and it says yes, the maximum clique size is 12 minus 8 is 4. So why are we doing this rather than putting the color band rule directly in the proof format? So the thing here is, coming up with a better bound is one of the ways that you write a new maximum clique solving paper. There are various clever tricks with coloring algorithms. You can do max at reasoning over color classes, for example. When we look at maximum weighted clique, where vertices have different costs, there are even cleverer rules, like you can split a vertex between multiple color classes. There are some really clever weighted clique algorithms that it turns out are trivial to justify using cutting planes. You literally just multiply a color class by its weight and it all magically works. And it seems that, for whatever reason, cutting planes is efficient enough to justify every clique algorithm that everybody has ever come up with. And these clique algorithms are not like SAT solvers, so every SAT solver does CDCL and pretty much exactly the same thing with slightly different heuristics. Some people are going to hate me for saying that. Whereas clique solvers really vary in what we do, so we don't want to have a proof checker in format for every solver. Okay. Are people happy so far? Looking at time, I will, since Jakob has already told us about this, I will go over VeriPB proofs very quickly. We've already said, okay, on status level, we're deriving a sequence of pseudo-Boolean constraints. The cutting planes proof system we've already seen. Unit propagation we've already seen. I would explain this twice so that you understand it better, but in the interest of time, we've seen this as well. Reverse unit propagation we've already seen. And I just want to come back to this key idea that reverse unit propagation forms a really good skeleton for DPLL and CDCL style searches, which a lot of solvers do, but they interleave it with stronger reasoning than some solvers. And it turns out that being able to interleave cutting plane steps with RUP gives you this really powerful framework for justifying a very wide range of solver behavior. Okay, not appearing in this talk, extension variables and deletions, which are the other two key features of VeriPB. End-to-end verification, we will hear more about this tomorrow. We were cheating. We were letting the solver tell us what the clique problem is. In the case of clique, this doesn't really matter. For some of the other problems we look at, the encoding is a bit less obvious. What VeriPB can do, the other question is, why do we trust VeriPB? So what VeriPB can do is actually run in proof elaboration mode, where it adds in hints about how to do RUP. It removes some of the convenience functions. It removes labels and replaces them with constraint IDs. Use this kernel proof. And then we have a formally verified proof checker, which we will hear about tomorrow. And it turns out once you have this framework in place, it's actually very easy to go from a final step of saying, okay, you don't have to trust the PB encoding. We're going to formally verify that the PB encoding means the same thing as the definition of a clique problem. This actually runs in practice. We can run a clique solver on a particular clique instance. It says, hey, there's a maximum of 17 vertices. We can ask the solver to produce a proof. Now, already here, we're seeing a very big slowdown in the proof production time. For this particular 200 vertex problem instance, I can produce a full round of propagation. So a full round of propagation is a single CPU instruction, which will be cached. So it's not even the cost of a memory access. Doing a coloring is about 150 CPU cycles. So already we can do an entire recursive call in less than it takes to call a single operating system call. So adding in I/O to this is going to be expensive. We can improve this number. I have not, this is using the C++ text formatting standard output stream. We can produce a fully verified encoding. We can ask VeriPB to check for proof. VeriPB says yes, 183 is the solution. This is a 200 vertex graph where the clique size is 17. And finally, we can run the formally verified checker. And the formally verified checker actually knows that, yes, this is a clique problem. So it gives you the output in the correct language again. But here, notice KPB clique only takes in the instance file and this proof. So it doesn't need to take in the encoding or anything else. So we've removed that problem. What do we need to trust? Ciaran will tell us more about this tomorrow. So all we need to trust is this definition of the clique and some slightly scary things saying if we run the proof checker on hardware and if it outputs the following, then. In particular, there's nothing about pseudo-Boolean proofs in here. So if you want to trust the verify, you don't need to know that we are using pseudo-Boolean proof logging. Okay. How much time should I spend on subgraph isomorphism? 15 minutes. Okay. Subgraph isomorphism is a bit more interesting than clique because subgraph isomorphism solvers do cleverer things. The problem is, given a little graph, which we call a pattern, and a big graph, which we call the target, find the pattern graph inside the target. This shows up in compilers, biochemistry, model checking, pattern recognition. This is a widely used problem. Quite often you want to find all matches. So quite often this is you want enumeration practice. So here is an example. This is not a unique solution. We can swap those two vertices around. There's another two solutions upside down over there. That's another solution. There's another one there. Have I missed any? Is that one? There's some more. I can't remember whether I've shown you all of them or not. So this is why we need these enumeration proofs.
What do the two colors mean?
Yeah, I'm being lazy, so I'm saying you can swap those two vertices around. I'm showing you two solutions at once. Okay, how do we express subgraph isomorphism in pseudo-Boolean form? We only have Boolean variables now. So I'm going to have one of these for each pattern vertex and for each target vertex. So if I map pattern vertex P to target vertex T, I'm going to set X PT to be 1. Otherwise, I'm going to set it to be 0. So for every pair of pattern vertex and target vertex, I have a Boolean variable saying this is a mapping. So every pattern vertex gets mapped to a target vertex. Every target vertex can be used at most points. If you stare at one of these constraints, you'll see that it's saying that the sum of the things is less than or equal to 1. The adjacency constraints are a bit more complicated. This is not quite the simplest encoding, but this is a relatively compact encoding that's still easy to trust. Either vertex P does not get mapped to vertex T, or vertex Q, which is a neighbor of P, has to be mapped to something in the neighborhood of vertex T. That's what I'm saying. So if I send a particular vertex P to a particular vertex T, if Q is adjacent to P, then Q has to get mapped to a neighbor of T. Okay, we have formally verified this encoding, so you don't need to trust that it's right. Here is one thing that a subgraph solver might do. I'm going to tell you, okay, vertex P has to be mapped to either 1, 4, or 5, vertex Q to 1, 2, or 3, vertex R to 2 or 3, vertex S to 1 or 3, vertex T to 1 or 3. And remember, we're looking for an injective mapping, so all of these have to be different. So for those of you who like solving Sudoku, what can you tell me? Yes.
4 vertices that need to be mapped to 3.
Yes, we have these 4 vertices, Q, R, S, and T, which can only be mapped to 3 things between them. And the SAT community, this is called a pigeonhole problem. SAT solvers can't really do this. Subgraph solvers do this all of the time. This is a pigeon in disguise. ChatGPT is quite good at drawing pigeons. Okay, so how would we justify this in a proof step? Matthew will go over a similar example to this in the next talk in more detail, so I'll just very quickly skip through and not justify to you why this works. But somewhere we have a constraint saying that vertex Q has to go somewhere. We have a constraint saying vertex R has to go somewhere, vertex S has to go somewhere, vertex T has to go somewhere. And we have these constraints saying we can use vertex 1 at most once, vertex 2 at most once, vertex 3 at most once. If you add all of these things up, so we're going to get 4 from there, minus 1, minus 1, minus 1, so we're going to end up with a 1. A lot of the things cancel, so we've got, let's see, an xq2 and a minus xq2. A lot of things cancel out, and if you cross out everything that cancels, the only thing that's left is a not x, p1. This is a 0, 1 variable. It cannot possibly be greater than or equal to 1. Remember the literal axiom rule? We can assert that any variable is greater than or equal to 0. So I'm going to introduce this. We can add these two together, and we have derived contradiction. So we have efficient proofs for pigeonhole principle problems. elements in cutting planes. Here is another example. Sorry. Pattern vertex P in blue cannot be mapped to pattern vertex T in any possible mapping. Why is this? So pattern vertex P has 3 neighbors, it has degree 3. Pattern vertex T has 2 neighbors. There is no way in any subgraph isomorphism you can map a vertex of degree 3 to a vertex of degree 2. In this particular case, we're trying to derive, okay, not xpt is greater or equal to 1. Okay. We're going to take our adjacency constraints, so x mapping to p tells us where q can go, p mapping to t tells us where r can go, p mapping to t tells us where s can go. We're going to take the injectivity constraints on u and v, so on our target graph vertices. We're going to take some literal axioms that I have sort of magicked up out of nowhere as to how I know which ones they are. And we're going to add these together. We get 3 times not xpt is greater or equal to 1. Divide by 3, not xpt is greater or equal to 1. So this is a sophisticated pigeonhole argument. We have to do a bit of work to uncover it. Yes, I wanted a twirly mustache. I'm not convinced about the missing eye on this pigeon. And this sort of looked a bit mysterious, but in VeriPB syntax, all we're doing is we're writing a poll line. We're saying take the adjacency constraint, saying, okay, if P maps to T, then where does Q go? The adjacency constraint, if P maps to T, then where does R go, and so on. The injectivity and injectivity on U and V constraints. Some mysterious literals and divide the whole thing by 3. We just do some additions and some divisions. So again, we are literally writing out text to a proof file. No pseudo Boolean reasoning inside the solver. In fact, to understand where these literals come from and where the 3 comes from, this is a bit of work for solver authors. This you actually have to do a bit of thinking about. Instead, what you can do is just add up the adjacency and the injectivity constraints. And then we have this IA command which says, take a previous constraint. I assert that the previous constraint implies not xpt is greater or equal to 1. And VeriPB will look at this, and it has a list of very simple rules to do with weakening literals and simplifying the right-hand side. VeriPB is actually able to derive on its own. Given the messy result of this sum, it can simplify and get us a constraint. And this is easy for solver authors to write because you know the left-hand side and the right-hand side. You know which vertices can't be mapped to which vertices. So at this point, all you need is a forward directing some text. Subgraph solvers do a lot of things. Some of these do not involve pigeons. We can do conditional injectivity reasoning. It turns out this still works. You do exactly the same thing. And a somewhat magical property of cutting planes is that you can pretend your assumptions don't exist, run the proof as if the assumptions don't exist, and what you end up with is the conclusion subject to whatever assumptions you happen to have. This is quite nice. We do distance filtering, so if vertices are a pair of vertices are distance 3 in the pattern graph, they can't be mapped to a pair of vertices at distance 4 or more in the target graph. We don't just look at the degree of vertices, we look at the degree of vertices neighbors. So this is pigeons with inside pigeons. We do path filtering, we do supplemental graphs. All of the techniques in state-of-the-art subgraph solvers, with one minor disclaimer, can be efficiently justified using cutting planes reasoning. And this is a bit mysterious. By efficient, I mean the length of the proof is roughly the time complexity for reasoning algorithms, so we don't really have to do any additional computations to be able to spit the proofs out. Okay, trickier things. There's a problem called maximum common subgraph, which is what do these two graphs have in common. So give me the biggest graph that is a subgraph of both of these two graphs. It turns out the way you solve this in practice is by reformulating it to a clique problem. So given these two, you somehow product them together to get this graph. You find a maximum clique in this graph and it gives you the solution here. We don't need to use this as the encoding. We can start off with an encoding of similar to subgraph isomorphism. So find me a mapping from the first graph to the second graph, except we say this mapping is partial. And we can do the reformulation inside the VeriPB proof log. And it turns out we don't even need to modify the proofs generated by the clique solver either. We can start off with the natural definition of maximum common subgraph, turn it into a clique problem inside the proof, run the clique solver without even telling it that it's dealing with a maximum common subgraph problem, and we get a proof of the original problem. I think Ruth will talk about this tomorrow. If we have this as our pattern graph, if a solution exists, then a solution exists where vertex C gets mapped to a lower number vertex than vertex D, because you can sort of flip the graph around otherwise. We might want to introduce this constraint C is less than D dynamically during search, or possibly even swap around which constraint we're using, depending upon what subproblem we're in. This, I think, is an open challenge. Maybe we know how to do this. Enumeration proofs are unsatisfiable except for all the solutions that I listed. But what does it mean when we want to counter enumerate solutions under symmetries? There's fairly clearly a right answer here, but getting this into the proof might be a bit tricky. Target graph symmetries, conditional symmetries. This graph isn't symmetric, but suppose that during search we managed to remove vertex 4 from every variable's domain. Then we would end up with a symmetric graph. Can we count when exploiting target symmetries and where some of these symmetries are conditional? This could be a very interesting challenge. Dominance. In the clique problem, suppose we have this vertex 2b. Every one of the neighbors of 2b is also a neighbor of vertex 2. So if you give me a clique that contains vertex 2b, I can give you a clique which is at least as big by switching vertex 2b to be vertex 2. So in this particular case, there is no reason to ever include vertex 2b in a clique. Some solvers do this, but they detect it dynamically. The question is how we justify this during search. Here is something else we don't entirely know how to do. So this is the one technique that is actually used in subgraph solvers in practice, and we can't quite efficiently prove logic. If a pattern vertex P and its neighborhood form a 5 clique, we cannot map it to any target vertex T whose neighborhood doesn't form at least a 5 clique. And we can proof log this, but what we can't do is do this in a generic way. We have to say a specific pattern vertex and a specific target vertex, whereas the solver won't do recomputations of clique sizes. For every pair, it will just calculate each vertex once. I don't think we know how to do this yet. Conclusion. We need a proof system that can express a wide range of reasoning rules efficiently. We have a lot of variety between solvers when we stop looking at SAT solving. We don't want to have a proof format per solver, but we still need efficiency. Cutting points can do this. Mixing RUP and explicit derivation seems to be a really powerful and easy way to get this. And we don't need a close coupling between how the solver works and how the proof system works. So in SAT, there is this very close coupling between solvers and resolution proofs. We don't need this. I claim that this is a red herring. ChatGPT is better at pigeons than maths. Stop there. Thank you.
Questions for Ciaran?
So I think that you can do all this because you are able, you as a human, to create the template for all the copy-paste operation you can do.
Yes.
So I think this works, and I think if you're able to translate for whatever things you are doing in your solver and do the right math, but this is what takes actually it's complicated in a solver is to do the right math, because what happens is you know what the rules you are doing, and you know that there exists a way to express them and you can generate them.
Yes.
I'm not familiar for all the features you have in a solver, but can you really express everything, or are there some features that you need to disable when you do plugin?
For subgraph isomorphism, we can do every single thing done in every solver that you could reasonably ever say is state of the art using cutting points, with the single caveat being a slight efficiency hit for clique reading. A year from now, when we have when Joe Lufney publishes a very advanced symmetry breaking solver, we might have to do a bit of work to catch up with it. But right now, we know how to do cutting points for every single thing.
And so I was wondering, so should all that knowledge be on the solver, or should it be in a more expressive language? So if VeriPB knew, okay, so this can be translated into a case statement, so I would just add a new keyword that says, well, this. So you know what I mean? So if you are a solver designer, you do not want every subgraph isomorphism solver designer to be able to do that not easy task of writing correctly all those maths.
So for constraint programming, we will be moving in that direction. I think Matthew is going to give you the talk that gives you all the advanced techniques. And so remember at the start of the talk where I said we could use these A rules, these untrusted assertions. The idea we have is we let solver authors produce these assertion rules, and they put a little bit of text hint on the assertion rule saying at most one. And then, so we take this proof, we trim it, and that you can still trim a proof that has assertions in it, it still works. And then we write another tool that goes through and it says whenever you see an A line that has this at most one tag, replace it with a cutting plane proof that does the same thing. Now for constraint programming, this is kind of viable because we have these notions of consistency. Like we can say, for example, for all different, I can tell you that for any possible constraint programming solving algorithm that implements all different, I know how to derive the cutting planes argument no matter what it does. And we can do this because we have this notion of consistency. For clique solving, it's a bit ad hoc because every paper that does something clever in coloring comes up with its own completely new reasoning rule as to how to do this. For subgraph isomorphism, there's a bit more in common between solvers, so again, we can do this. The question here, I think, comes down to how creative solver authors are. If it's recovering at most one constraint, yes, we can write a tool that fixes your proofs for you. Yes.
So, but the last section, is these problems or methods that you don't know yet how to express in VeriPB, or that you know that they're not possible with the current tooling of VeriPB, or is it things you already know how to express in VeriPB?
For symmetries, I think 6 months from now, Ruth's PhD student will have taken my solver and put in some really, really clever symmetry reasoning into it. I know like 70% of what he's done, but he's done some more clever things that I don't understand yet. I believe there is a viable path to VeriPB proof logging for everything he's done, but I will need to sit down with probably Marcus, Jakob, and Ruth and say, okay, are we sure about this? the clique neighborhoods we know how to do, and we know of a plausible extension to VeriPB for doing it efficiently. The difficulty is how you add lemmas into a proof system in such a way that they are compatible with symmetries. Because as I understand it, you can take VeriPB, including the symmetries, and that's sound. You can take VeriPB plus lemmas, and that's sound. But if you take lemmas and symmetries simultaneously, it's not sound. At least the way we would do it now. Yeah. So that's a challenge. Okay.
You said that everything is possible efficiently, but I was wondering, are you not getting overhead in step one, where you introduce all of the variables for all possible pairs?
Yes.
Does the solver also do that?
No, the solver uses these bit set data structures, so the cost is quadratic. But yeah, this is actually the expensive bit is writing out the adjacency constraints, because the adjacency constraint encoding is cubic in size, whereas the solvers don't explicitly store the adjacency constraints anywhere. So a very long-term extension to VeriPB could be to allow these quantifiers inside VOPB file. So you're sort of saying, okay, here is a template for creating a constraint, apply it to the following lists. The somewhat interesting question is whether you can do rep checking and redundance checking and so on without explicitly expanding to quantifiers. Which again, I think is, if we get a really, really, really good PhD student and have them do that and nothing else for 3 years, then yes. Yeah, but then like the clique the encoding size will kill you, because if you give me a large sparse graph, writing out all the non-edges, you die. So yeah.
So does it mean you don't need those non-edge constraints, or not all of them, for the ROP? So if you do it in the hinted format, right?
The difficulty is, so the solver somehow, so whenever it produces a coloring, it's implicitly relying upon the non-edge constraints being valid. But the solver just stores either an adjacency list or an adjacency matrix. So the size of an adjacency list encoding only depends on the number of edges. And because we know that the coloring algorithm is valid, we can write a coloring algorithm that somehow is efficient in the size of the number of edges, whereas the proof that we write out is efficient in the size of the number of non-edges. And if those two things don't line up, there's efficiency hit there.
But the coloring relies on the knowledge. Oh, if you didn't tell me there is an edge, I can infer there is a non-edge.
Yes. So could we, in a templated OPB file, potentially say for all pairs except the pairs appearing in this list? Maybe. I think this is a good PhD student. 3 years, it's a solved problem kind of question, but yeah.
Okay, I think we should thank Ciaran again and move on to the next speaker.